Okay, so I think that we can start. First of all, thank you very much to everyone for joining us, especially with a lot of activities scheduled at the same time. So yeah. This workshop is called Application of SSbD Framework to Polymeric Materials. This is a framework workshop organized by the 4 projects: REPurpose, SURPASS, REDONDO, and ESTELLA. This project has been funded under the same topic, which cover the different application of this framework to these polymeric materials. As you will see in the following slides, different perspectives, different point of views can be applied to this polymeric materials field in order to create safer and more sustainable materials. Unfortunately, Belén Monge from AIMPLUS can't join us, so I will go to her slides, okay, very broadly, because I'm not an expert in the REPurpose project, but at least to have her feedback and her comments, okay, in this topic. The idea is that every one of us will present a bit the topic, the main conclusions, the potential gaps in the SSbD framework, and then after the presentations, more or less 15-20 minutes by presentation, we will have a discussion, okay? It's a kind of round table, but of course it's an open discussion. So please, in this part, feel free to share with us your comments, your questions, whatever. Okay. So first of all, the first project is REPurpose, and this presentation is focused on the application of the SSbD framework on this project. These are more or less the main features of the topics, the funded and the partners that are involved in this project, and the main concept of this REPurpose is the development of building blocks from different waste, plastic waste and paper cardboard, through the enzymatic depolymerization and fermentation. With these building blocks, REPurpose can create new polymers, okay, or develop new products. Once this product has been developed, they can be recycled by enzymatic recycling and to biodegrade these materials in order to get again these building blocks through the fermentation of the bio-based feedstock. The methodology followed by REPurpose, of course, is the Commission recommendations published on the 8th of December of 2022. That is the SSbD framework that everyone knows. So first of all, they have been applied an evaluation of the most critical additives used in these polymers, okay, through the ECA inventory, but also using another databases like ECHEMPortal, the EPA Ecotox, ChemAgora, ChemView, Comtox, and other databases. And the main key aspects, the main gaps that they have found is that perhaps from these 418 additives, the 58% were not even under regulatory scrutiny under the REACH. Even and 11% remain without any information, and the 6% had functions that were outside of the scope of the project. these most critical additives have been compared relative release potential through molecular weight, vapor pressure, solubility. So practical guide describing uses of additives that not cover certain things like the compounding, light installation, and maintenance of the articles of complex objects. Even there is a lack of information for several polymers in other practical guidelines. So the repurpose strategy here is to have a direct contact with the companies and an association, including for the most critical additives, this search on the relevant information in the ecotoxicity databases, scientific bibliography, use the food contact regulation, even software, QSAR models, and so on. So this can be applied to the development of, this commission recommendation can be applied to the development of new chemicals and materials, and also for the reassessment of the existing one, as we already know. So there is two phases, the phase of the redesign and the phase of the safe and sustainability assessment across the different steps of the life cycle. And we have these three different levels: the molecular design, the process design, and the product design. So the idea is to see what is the material efficiency, especially for the reuse and the recycling, to avoid the use of any hazardous chemical or material, to use renewable sources, minimize emission, the end of life. Then this second stage is more focused on the safety and sustainability. This picture has been extracted from the SSbD framework. And then this step 4 is more based on the environmental sustainability assessment. So in this project, there has been performed a function-based LCA, and they have calculated the environmental footprint. That consists of a minimum sets of impact to assess. And some of the key findings in this project is the regulatory compliance is essential for the sustainability, but at the same time challenges due to the diverse of international laws, the reach and the material toxicity, widespread knowledge of regulation with varying influence of material choices, the additives and the substitution. Many companies have eliminated harmful additives and found alternatives. The renewable materials has a strong interest using the renewable materials. The bioplastics bioplastics have a limited use due to some concerns about the performance, even costs and regulations, and the end of life focus on the design of products that are reducing and recycling. So the main conclusion is that the industry is shifting towards sustainability, but challenges remain in harmonizing regulations and adopting bioplastics, and companies that adapt proactively can gain a market advantage, but this requires technological innovation and industry collaboration. So the main challenge that we have to address is to identify and replace hazardous chemicals in polymeric materials with safer and more sustainable alternatives without compromising their functionality, to ensure that polymeric materials are designed to minimize their environmental impact throughout the life cycle, from production and recycling or final disposal, without forgetting any stage of the full value chain. Enough databases information about the raw material used to carry out an exactive LCA it's not clear, and is regulation pushing biodegradable or bio-based material development or more recycled materials? and of course the social perception awareness. So that's it from the slides from Belén. So the next project is Redondo. So please, Javier from ITENE.
So, hello everyone, thank you for being here. I'm Javier Alcodori from ITENE, and I'm going to try to explain how are we applying the SSbD methodology for Redondo project. So, Redondo project is a project that started in 2022, and we are trying to get a cross-linked polyethylene from different new synthetic pathways, and with the intention of giving new properties to these REPEX and trying to make it more recyclable and sustainable. The specific objectives of the project are, as I said, with these two synthesis routes, trying to get the crossing polyethylene, incorporating green additives to this polyethylene to give properties as flame retardant, antioxidant, and mechanical strength, and then improve the recyclability of this crossing polyethylene. In this sense, we also want to make these new polymers safe and sustainable by design by identifying hotspots in the life cycle of the polyethylenes, investigate toxicological effects, and also develop a placement tool to integrate all the findings that we get. This is the state in the project where we are right now, and an overview of the consortia. So, how are we implementing the SSbD methodology? We are following, obviously, the framework that has been developed by the European Commission, and we consider it important to gather information from the material producers in order to assess the properties of the chemicals that are being used. Then we perform occupational health and safety assays. We try to computationally establish where it's more important to perform occupational measurements, and then we perform them to improve the safety of the workers. Then we want to establish the likelihood of exposure to the chemical or material once the product is developed for the final user, and finally implement the environmental sustainable by design assessment. Okay, so well, as I explained, we are using the framework, and we are also developing a scoring system that allows us to know how good or bad in terms of sustainable by design a material is, and to allow us to decide which is the best alternative or strategy to be applied. So this is an overview of how are we performing the first step of the framework. First, we try to establish how is this material or this chemical, the legal status of this chemical material by REACH and CLP regulations. Then we try to gather additional information in the case we find that there are some data gaps in these chemicals. We do this by bibliography, computational models, and validated until a certain extent with the experimental data. We also try to take a look at the safety data sets that of the product that the material developers are using, and then we perform another analysis data gap. In the case we found that there is information missing, we try to go back and try to get this information from the sources that we can. Then we propose an action in the case that the chemical may be found or the material may be found toxic or hazardous or whatever, and then we perform this assessment again in order to find more data gaps or getting a score of this new material or new design of the material. For the second step, we use the data we gathered from the first step, and we also gathered some new data in the categories that are needed, for example, for the likelihood of exposure for workers. Once we get this information, we perform a process risk classification, and we computationally estimate the potential exposure of workers to hazardous chemicals or materials. If this is found, we may validate them by performing monitoring campaigns in the place where the material is being developed, and then we propose some actions to reduce the risk for workers. And then, again, as it is an iterative process, we try to reassess again these hazardous or these hazards that may have the workers. For the third step, we evaluate the migration of the chemicals during the use phase. What is the likelihood exposure for final users? Then we evaluate how these chemicals or materials are migrating to the environment, and we also do this for the end of life. Then we, with this data, we try to assess the concentration, the hazardous, how hazardous can be these leaches or these migrations to the population and the environment, and then we perform also some actions in order to reduce these effects. And finally, for the fourth step, we gather information from production routes, from different use scenarios, and from the end-of-life scenarios. We assess the sustainability impact of the product to toxicity, climate change, pollution, and resources level, and we try to also propose new actions to improve the performance of this material or chemicals. And then we assess again to get the most sustainable, in this case, material or chemical that we can. We also perform some toxicity essays in order to know, to generate new data on materials, polymers, or chemicals that are being used. And for example, we perform this assay with two compounds that are being used for the same process for producing the RPEX. Before the SSbD assessment, we performed this cytotoxic ecological analysis, and we found that the product was really cytotoxic to the cells we explored, which were A549 for lungs and HACAT for dermal exposure. We proposed with the material developers, who are the experts, to substitute this material, and we get this new data, which proves that the cytotoxic effects are highly reduced with this new chemical. We also tried to generate this data for genotoxic analysis. Unfortunately, we found no differences regarding the genotoxic properties. So the product was cytotoxic but not genotoxic. And we also did the same for the production of interleukin-8 in order to get a marker for inflammation. And we found that the product was not making the cells generate more interleukins-8. For the occupational health and safety, the occupational exposure assessment, we perform, as I said, two steps. First, a computational assessment of how we estimate that the exposure is going to be, and then we perform experimental monitoring campaigns. We place different equipment at different distances and try to establish what are the dangerous properties for the workers. For example, for this process, we found that there was one high risk of inhalation in one process. Here was medium risk process for this synthesis process, and the rest we detected that there was not likelihood to be an exposure for workers. Regarding the step 3, as the project is still ongoing, we're still working on it. We're trying to use different computational platforms to estimate the exposure of the product in the use phase. And then, as I said, we will try to develop more strategies for improving the safety. Regarding the sustainability, this work is being done by ISQ in this project, and it is divided in 4 different steps where we set the goal and the scope definition of the LCA analysis that we want to apply. We also develop a lifecycle inventory where we get data for different sustainability aspects. And we also get this data by questionnaires to the partners on the project. Then we have where the life cycle impact assessment is performed in order to get the sustainable impact, and then we interpret the results. This shows that we are analyzing raw materials for all the steps of the production of the RPEX, and we establish where the different materials are involved. For the life cycle costing and the social LCA, the same process is being done. We establish where its chemical or material could affect, and we analyze this. In Redondo, we are also performing, we're also developing an inventory database with all the findings that we are getting from the additives that are being used in the process. And all this data that we are generating is going to be integrated in what we call the PlaceMe tool, which will take into account all the circular value chains structure that is taking place on the project, all the model formulation and optimization code that we are developing to guide the synthesis of these RPEX, and then the goal is to get a web-based platform with all the data generated in the project. So this is how the PlaceMe tool will look like. Our colleagues from Axia are developing the tool. Our colleagues from IMEN are developing the additives inventory with the help from ITN, which as us and ISQ, and RDC will perform the development of the web platform. So the conclusions is that this is a tiered approach that will allow us to get safer and sustainable polymers with a reduced impact on health and environment. The results obtained from the framework implementation, this will be the evaluation, will be incorporating in the PlaceMe tool, and with the experience that we gain through this project, we will try to implement and develop strategies in the polymer sectors towards a greener transition in the chemical strategy for sustainability. And thank you all for your attention. And if you have more interest on the project, you can scan the QR codes or go to the webpage where all information is available. And also I want to thank to Thessaloniki and from the University and European Union for funding the project. And that's everything by myself.
So, good morning, everyone. I'm Socorro Vasquez from LEITAT, and we are involved in the SSbD implementation in SURPASS. CA is the coordinator of this project. So I will show what was the approach of implementing the SSbD in this project. So first of all, this is schematically how SURPASS has been organized in three, let's say, three big main tasks, which were the material design, so designing something for being recyclable in the polymer area. And then there is another big block on the assessment, on safety and sustainability assessment. And then there's another big block on the recycling technologies applied to the materials considered in this project. And concerning that, so these are the case studies or the materials and case studies that SURPASS focused on. So we target three sectors, so transport, building, and packaging. And in the transport, the main aim was to go for lightening the epoxy bitumer and to replace metal parts for the train structures. So the building, so the bio-sourced polyurethane resins with enhanced properties, replacing the PVC for window frames. And in the packaging, so the multi-nanolayer films to be replaced for multi-layer films for food packaging. So if we consider these case studies, we apply solutions based on this block of, as I said, the design phase. So we apply design principles to the cases. So here in the upper part, I show the situation, that is the current situation. And then in the lower part is the solutions given by the SURPASS team for designing something that is in all the value chain, has some safety or sustainability improvements in there that will be considered from the beginning, from the design phase, to come up with safe, sustainable, and recyclable by design materials and products. So in this case of the transport case study, the target of what it has been done by the designers, the material designers, is to provide halogen-free flame retardants with recyclability properties for the end-of-life management, and also some less processes with less energy consumption, and also shorter times, and so energy efficient, more energy efficient and weight reduction in some of the materials for final products. And as I said, with the main target of recyclability in the design mind of these proposals. The same for the building case study. Here, the idea is also to use bio-based polyurethane to substitute these fossil-based window frames. So for this, with halogen-free also flame retardants, and recyclable possibilities for the end of life, and also safer processes towards zero waste approach. And then in the packaging case study, so we also applied these new formulations with decreasing the amounts of the percentage of recyclable content of the materials, playing with the layers and the thickness, reducing the percentage of this material that we need to reduce, and try to recover and provide some recycling efficiency, so reducing the landfill waste. So these are the overview of what the first block of design, the material design people was working on SURPASS solutions. And then the teams for applying to see if these solutions proposed by SURPASS are safe, sustainable, and recyclable by design. So this is to show that the whole team involved in this work has been distributed, or we distribute ourselves in different expertise, and also covering different steps of the JRC framework for the implementation of this framework. So we have teams dedicated to the hazard dimension, teams dedicated to exposure dimension in the different steps, and then the LCA and LCC people, the sustainability blocks. And then we how was the steps to follow? So we first following the collection of what are the status and what is the data available and at the beginning and the current situation. And then we identify data gaps, hotspots for exposure, and identifying what are the hotspots in the whole value chain, and also the identification of all the data from the inventories of for the life cycle and the sustainability assessment. Then the next step was to provide the scenarios and the modeling for impact and cost. And then if we need to provide some data that is not available, then we perform all the studies to produce and come up with the results that we need for this assessment. So the hazard data, the exposure quantitative data, and the hotspots and the impact indicators that are identified in the sustainability part. With all this, we got scoring for each of the dimensions, let's say, and the final results that we want to come up with is to integrate all this scoring to facilitate the decision making for the sector, the plastic industry. And with this infrastructure to provide this scoring system as a tool for them to follow. So I will show some of these steps. So for the dimension of, let's say, hazard assessment, which covers the different steps of 1, 2, and 3. So we gather available toxicity data, optimize also and perform some toxicological testing that was needed because the data was not there, and trying to link these physicochemical properties to toxicity outcomes. So the data was collected in different, let's say, steps. First is existing data from all the resources that we could have access to, and all the available databases. And then the second step was using in silico methods And then there was some also experimental work done for in vitro testing to generate the data. And in that sense, we focus on 3 different routes, inhalation, dermal, and oral, 8 different endpoints, and in the endpoints, so we target this cytotoxicity, genotoxicity, oxidative stress, inflammation, and epigenetic data, endocrine disruption, and acute aquatic toxicity. So these were the target endpoints and experimental work focused. When we go to the exposure assessment block or dimension, we, as I said before, we first launched a questionnaire, adapted questionnaire to these areas and to these the specific of SURPASS case studies to identify the hotspots, which I think is a key step that we have to do to identify which are the substance materials and their potential transformations when they are released and emitted to any target species, let's say. And then we do, with this identification of hotspots, we can identify also which are the data gaps that we have based on the existing data, and to plan all the experimental tests to simulate exposure scenarios and generate this data that is not there, or quantify releases with exposure for the exposure assessment purpose. And then we integrate, as I said, exposure, hazard, and LCA outputs in the infrastructure. The questionnaires were developed to identify these hotspots, so all possible exposure routes, and all the we identify also all the guidelines that are for release and exposure of chemicals on the different target populations, and specifications of the polymer. So that's important to work with the actors of the partners in the project that knows a lot about the specifications of the polymers that we are working with, and the alternatives that were given in SURPASS. So then I wanted just to emphasize that it is really key to identify all the hotspots, considering the whole value chain. And here is a general scheme how all the release materials and emissions can produce an exposure in all the compartments, including human and environmental compartments. And so this is quite key for the assessment to identify these releases, because we can actually reduce release and emissions to limit the potential exposures, so that reduces also the production of hazard data, which is quite the expensive part of the assessment. So we can apply and act in the source of emissions to target this reduction of safety issues or impact on the human and environment. Or we applied risk mitigation measures at the source as well. So these can be the two strategies. When, well, I just show two examples of how we identify these hotspots, which for us were quite key, and also key for information for the hazard people to actually be more specific on which is the data that we have to generate in each case. So with exposure scenarios, so the activities that are taking place in each of the steps of the value chain, then we can identify which are those potential hotspots and then plan if there is any experimental work that we have to do to generate that experimental data, and to see which are the target substances that we want to trace. And here is the example for the packaging, and we have also the example for the other case study, but just to show you how we did this for all the case studies. I didn't want to go into more detail. And then when we go to the sustainability part, so here, the colleagues from the sustainability part did evaluate all the case studies also, and they were basing this assessment on the comparison with the technologies, the current technologies and the current materials that are used, and the benefits of the solutions given in SURPASS. And of course, they were first working on the inventory data, and then the modeling of the impact categories, and then the environmental hotspots versus the reference material. For the costs, also the life cycle cost strategy is they have parameters that are aligned with this life cycle assessment as well. While the functional unit, the system boundaries, and all the inventories that are used for all the case studies in parallel for life cycle assessment and life cycle costs, and all the categories that have been included in the cost assessment. And the integrated approach for SURPASS is to integrate those 3 dimensions or 3 blocks of safety and sustainability, and put them in an infrastructure. So we will have a scoring-based assessment to guide the stakeholders to design safe, sustainable, and recyclable by design polymeric materials using this digital infrastructure that is still in development now in the project. We did the first, we are in the first steps of developing this infrastructure with the feedback from the different areas of hazard exposure and sustainability scoring outputs to integrate them here in this platform. So this is all. I would like to thank all the partners, and of course I'm not covering all this myself on my team, but many teams are involved in the safe and sustainable by design implementation, and all the partners of Work Package 4 of SURPASS are thanked for all these contributions. So thank you very much.
So the last project is ESTELLA. So now I can introduce myself. I'm Alberto from IDNR, and I work in the SSbD implementation in ESTELLA. This presentation is more focused on the safety part and ensuring the safety of polymeric materials through the application of the SSbD framework for this this project. First of all, going to the concept of ESTELLA, the main goal is to design of new recyclable epoxy resins to present a solution for the environmental problem of low recyclability rate of traditional thermoset composites. So the idea is going through new technologies like the covalent adaptive network, okay, to design new thermoset matrices. So from these fossil and bio-based epoxy resins, we can create new matrices that can be adaptive or dissociative, okay, in order to improve their recyclability. So this is based on two main new technologies. The first one is the CAN, this covalent adaptive network that can be associative or dissociative. And we developed these thermoset resins, as I said before, from fossil monomers or even extracted from biomass, with the inherent recyclability properties, because in the end it's like a puzzle that you can build in new structures, okay, and then you can recycle all these blocks. And finally, the functionalization of the natural fibers, okay, with the aim of ensuring the suitable adhesion with the thermoset materials, and to is the recycling designed for the manufacturing of biocomposite of key market application. So this is more or less the idea of the project. And then we have, as the other project said before, the SSbD framework. So I will go very fast, but the most important thing is, it's true that this project started just right before the publication of the SSbD framework, but it's true that the work package that is in charge of the safety part starts just in the middle of 2023. So the case study report had been submitted just before this work package started, and then the guidance document was released in the next year. So we have been adapting the project and the approach for the safety and sustainability according to the new updates of the framework from the European Commission. So the general idea is that there are five main steps. The first steps are for the safety dimension, then the fourth for the environmental dimension, and the final one for the social and economic dimension. In this presentation, I will go deeper in the step one, especially because the idea or the perspective of this project was to predict toxicity. So the idea is to develop in silico methods to predict the toxicity of the new materials developed, and then to address, of course, the exposure and the risk assessment also with computational tools. So with this perspective, we create this boundary system. You can find the template for the boundary system in the guidance document for the implementation of the SSbD framework. So in this case, we consider the thermosetting composite as the real innovation of the project, and then the main objective for the hazard assessment. Okay, the rest of the task was included in the step 2 and the step 3 according to their use, or even their recyclability, because recyclability in this project is a crucial part. So we included the recyclability part in the step 2, because in the end is something that you do in the industry. So to study, of course, the safety of the workers, the occupational emissions, and so on. Once we have done this, for the step 1, this is the main workflow of that it's expected for the step 1. So first of all, we gathered all the existing information, especially for the safety of the main components, with this idea that the safety of the final product is the safety of the main components. And then we apply a tier 1 with the QSAR development for the new structures. Okay, this is the idea, to gather information of certain additives, certain chemicals that are involved in all the chemical process for the development of these new thermosetting components, but in the end to evaluate the intrinsic safety of these resins, of these thermosetting materials, with the development of QSAR models. So here I'm going to present some challenges and difficulties that we have to address to overcome this this problem. First of all is, okay, the framework is focused on chemicals and materials, but for polymers, it's true that the polymer is not a material itself. It's perhaps closer to a chemical, because polymers have a chemical structure, but the main properties, the main feature of the polymers are closer to properties than a material, than a chemical. So perhaps there is like a gap in the SSbD framework to assess this kind of materials, of or chemicals. So when we address this, the implementation of the SSbD framework, we don't know exactly if we are covering as a chemical or perhaps as a material, especially for the features that we have to take into account to evaluate their toxicity. And the second main challenge is the lack of data that exists in the polymers, especially for all the toxicological information. There are a lot of databases, a lot of data in general about polymers, but the vast majority of this data is focused on physicochemical properties, and to find this data of toxicological properties is really difficult, especially because we have fossil polymers, we have bio-based polymers, so within the polymeric material fields is a very broad field. So in the end, there is a lack of data if we want to develop new predictive models. So different proposed solutions that we are proposed through the project. First of all is in the way that we understand the polymers. First of all is, okay, we have to calculate the toxicity of the polymers, but perhaps we can focus on the toxicity of byproducts, these non-intended added substances, TIFNIAs, that can be produced not only on the in the end of life of the product, but also in some compounding phase, for instance, in the formulation of the polymer, but also to be very focused on the toxicity of the additives, because sometimes the hazard is not on the polymer, especially for bio-based polymer, because these kind of polymers, to keep their functionality, they introduce some kind of additives that can be more hazardous than the polymer itself. So the idea is to develop these machine learning models to taking into account of all these points. Okay, first of all is to predicting toxicity of these potential byproducts, creating an applicability domain with similar compounds. Okay, so we know that these kind of machine learning models like QSAR are better for in the relationship between the structure and the activity of chemicals. So if we found similar structures, we can create an applicability domain where we can find the potential byproducts. So we will have a model for to study all these non-intended substances, all these byproducts that can be being created in some step of the life cycle of the polymer. So this is one of the ideas. Then is to understand the difference between the toxicity of the monomers and toxicity of the polymer, because if we know the toxicity of the polymers, we can link the toxicity of this polymer with the structure of the monomer. There are some studies about that, but we have to be very careful, because if we create QSAR models only for the toxicity of a monomer, it could be not the same toxicity of the polymer itself. So we have to use data from the toxicity of polymers and not for the chemical structure similar to the monomer itself, because the interaction of the chemical part of this monomer is not the same of the polymer. And finally, and perhaps the more interesting idea, is to search in these physicochemical properties that can be related with toxicity. There is a lot of data about the physicochemical properties of polymers. So if we can relate this toxicity of polymer with certain features, certain properties of the polymers, physicochemical properties, these physicochemical properties can be predicted better than the toxicity. First of all, because there is a lot of data, but also because some in silico models like molecular dynamics can be very useful for predicting this kind of futures. Okay, and it's true that in this way, some computational simulations can be not. Yeah, it's not the best option for calculate the toxicity, because there is unless we have an information or a knowledge about some molecular-initiated events or some interactions. Okay, we are not able to calculate toxicity with of polymers in this way. So the main conclusions of this presentation, and we will move on to the open discussion, is the first of all, the specific framework for polymers, a theoretical specific framework for polymers would be a great support for us, considering the specific nature of these materials. Because perhaps there is a lack of data on how we should address this problem, especially because it's not just the toxicity itself of the polymer. Perhaps the polymer can produce some kind of micro and nanoplastic, and this is another topic for another specific workshop about the toxicity of micro nanomaterials, because there is a evident lack of knowledge in this field. Of course, there is a lack of toxicity available data for polymers. So perhaps we need a way to address this lack of data, and also intrinsic properties is not enough to define the polymer, because if we have a chemical structure like an smiles, this not define the polymer itself. There is some parameters like the molecular weight, the size of the polymer, specific properties are also involved. Okay, the polymerization, whatever. And finally, that the polymer itself could be not the problem. As I said before, additives, byproducts, a lot of things that are related with the polymer, but it's not the polymer itself, could be worse than the polymer itself. Okay, so this is the main conclusion for us, especially for the application of the machine learning model and toxicity predicting approaches, okay, for toxicity. And yeah, that's all from my side, okay. Yeah, you can. Okay, so now I think that Javier and Socorro can move here with me, and we will move on to the open discussion. For this part, there are like four main topics that we are going to discuss. If you want to contribute, to ask something, please feel free to do it. Okay, so the first part, I would like to ask you if you consider that are some gaps, okay, in the SSbD framework for the polymeric application, especially for the cases of our European projects. Socorro, do you want to start? Do you think that the SSbD framework is enough for the implementation of the SSbD approach in the polymeric field?
To me, yes, I think I think that the framework is a guidance of how to integrate these dimensions in the innovation process. So I think it's the how and the methodologies to apply this into any sector, I think is more flexible, and I think the flexibility is there. But I think what is the framework and the safety and sustainability considerations that are recommended, I think it could fit in this sector or this big plastic area as well as in the other sectors. I would say that maybe there will be some more difficulties when we're talking about biocides, for example. But when we're talking about plastics, it's I would say that there's no need to change this recommendation of the framework. I think is to work on all the aspects that we have to cover on these big dimensions of safety and sustainability to facilitate for the industry. But I don't think it's or industry or all the actors that they have to implement it to make it easier for them. But I think what is the structure and the dimensions is fitting to me clearly to this sector.
Okay. Javier, you want to comment anything?
Yes, I kind of agree with Socorro. I think it is a good starting point for assessing the polymers, but I think that for these kind of chemicals or materials, there should be something a bit more specific for them, because it is not easy to say if a polymer is or not hazardous, which is the first step, because the polymer can be from an oligomer to a really long chain of the same monomer. So what is dangerous in the polymer? The monomer, the oligomer, the low molecular weight, the high molecular weight. When assessing toxicity, what are we assessing? The monomer, the polymer, for the same for the QSAR models. So sometimes it is not that easy to evaluate the hazardous properties, which is the first step. So I think that maybe we could all work in trying to improve the framework or the recommendations, trying to adapt to these in a way strange chemicals or materials, or at least not strange but different.
Yeah, that in the end the framework itself is not obviously the problem. The 5 steps are perfect for the assessing this kind of material. Perhaps it's the way that we address every one of the steps, because the step of collecting information in the step 1 perhaps is more difficult, or we have to take into account more dimensions of the polymer, because we have the chemical structure of the polymer, we have the molecular weight of the polymer, even we have the size, because perhaps this polymer creates, as I said before, micro and nanoplastics, and then the problem is not the chemical structure, the problem is the size. That we have a lot of things to take into account, that perhaps in a chemical we only have to assess the safety of the chemical, and it's easier to prove that this chemical is safer or is not safer enough or whatever. Okay.
Yeah, to me, I think it's not related to the framework. I will say it's more related to how to address hazard in a complex material, which we had this for nanomaterials as well, advanced materials. The complexity is so high that you have different dimensions that you have to cover when you are addressing the hazard of complexity or a mixture as well. And in this case, for plastics, the adaptation of testing and all these things is limiting the data available on hazard of all potential transformations or all potential components of a polymer. But I think it's a more a hazard assessment problem than the framework itself, considering the implementation of this safety. I think it's always, as I said, I think it's in terms of methodology to apply, which, I mean, the guidance document on the methods is an orientation, but of course is flexible because you cannot generalize in sectors.
Yeah.
And I guess what is, I think, positive is to be focused on sectors, and the regulations of the sectors will also facilitate our work in producing data and following their restrictions in terms of the regulatory frameworks they have to follow. But of course, is something that you have for each sector and each material. I think you have to see that there will be difficulties in some way or the other. And I think one thing that we are focusing a lot is maybe the hazard, but also we have the other dimension of the safety, which is the exposure, so that we can also see if there is no way to tackle it from one side, we can tackle it from the other side. So I think, I wouldn't relate it to the framework, per se.
Yeah, it's important to highlight, especially for the audience, that the final goal of this collaboration between projects is to release in the end a kind of document, a kind of report, a kind of guidelines, okay, for the implementation of the SSbD framework in this field. Okay, this is the idea, and it's expected to be released by the end of the year. Okay, so this workshop, this discussion is part of this collaboration to, in the end, once the project are closer to the finished state, to release this document, especially to support the work of the people from the SSbD and so on. Yeah, there is a question. Well, not the polymer itself, because each project develop different, apply the SSbD framework from a different perspective. In my case, in STELLA, for instance, we develop new ways to create thermosetting materials from these from these resins. So it's the way that they are connected to try to connect it and disconnect it from the recyclability. But for instance, in the SURPASS case,
yeah, we have different polymers in the different sectors, so we have covered different. So I think for the 4 projects, there will be difference in which are the target polymers, but this goal topic was more about targeting the to get polymer or plastic materials that were more recyclable, so that you introduce the circularity into materials that are plastic materials that are in different sectors or different areas. So each project, of course, is focusing in different polymeric materials, as you said. So no, I think it's more about assessment of alternatives to the current materials. So we are seeing if we can influence the innovative materials to be more recyclable based on introducing safety and sustainability as one of the parameters in your innovation. So I think it's more about the new alternatives, but not the current. It's a comparison, of course, with the current situation, but the current situation sometimes, as you said, you do have also gap data, that gap analysis. In the gap analysis, you find that there's data gaps that doesn't allow you to assess everything that you have there. And also, as we were saying, the complexity also of the existing polymeric materials is the same. So the hazard assessment, you will have the same problems of seeing if the additives or if it's the polymer or if it's the components of the polymer which produce these hazard impacts in the different parts of the value chain. So I think there is data gaps in the current situation, and then
in the end you can apply the same workflow, even the same framework for the current materials if you know all the composition, all the features, all the.
In my opinion, you are right, but there is a problem, in my opinion, with polymers, is that sometimes if it is enough big to not being bioavailable for cells or biota, it theoretically
it
theoretically will not have safety impacts. Once it is bad, for maybe regulation could be improved to consider also, for example, what Alberto explained, the degradation by products of the plastics or the microplastics or the available fraction of of these polymers in order to trying to assess different points of the life cycle of the polymer. But
one thing that, for instance, the current framework covers is the availability of certain compound or certain chemical of a material, because perhaps there is no possibility to any release of this compound, and then we can consider as a safe material, because there is a high value of hazard, but a zero value of exposure, then there is no risk at all. But for instance, in the polymeric case, in the polymer case, there is a lot of possibilities of secondary exposure. There is a possibility of byproducts in the end of life, but in the end of life we can also the creation of the release of micro and nanoplastics and so on. And yeah, as I said before, is obviously one of the great concerns of the European Commission. There is a lot of funded project on micro and nanoplastics, but yeah, perhaps we can start to consider the safety of a polymer, not only because, yeah, it's a polymer, it's really big. There is no biological availability of this polymer. There is no possibility to go to the human body and so on. But in the likelihood to create these secondary products, you know?
Yeah, but also yeah, because a polymer per se cannot already be viewed as a material, right? Because without the additives, they cannot perform most of their functions. So I would say that probably it would be, I mean, to me, it's quite obviously necessary to extend the idea. Like if you have a material, you cannot only look at the polymer.
Yeah.
Because then you also wouldn't have the functionality. It's a system. It's a system of a chemical system that surpasses.
Yeah, and right now, I think that for all the projects, the study of the additives is one of the key points of our assessment, because additionally is easier for us because there is a lot of data. You can go to any database like Comtox or ECA or CLP, whatever, to understand the hazard of these additives. This can connect with the following part, and is the differences that in the application of the SSbD framework for the chemicals and for polymers. Yeah, you can follow with this question, but in the end, I think that it's more related with this part. Please.
Okay. No, I just wanted to say that I think SSbD is not there to solve the problems of the hazard assessment of data that is missing from the polymers, I will say. Okay. So I think I don't think we will be solving that problem, because the problem of not having data is to produce the data. And I think many, as we say, many of the projects that are working on microplastics, they are producing a lot of data on hazard of polymers, additives, and all the exposure relevant materials that are coming into place during the value chain of some of the plastics that they consider in their projects. So I think those projects are more related to producing data on polymers. I guess there is more polymer specific hazard projects that are producing this data. So we rely on data generation, as you said, that now the regulation is not there, and then you don't have to produce it. At the research level, you produce that in some projects and in some of your daily work in some of the labs. And we have to rely on that the data will be available somehow via databases, but we don't know. We cannot promise from our side. And of course, we produce some data in our projects as well, because we found that we don't have it. So we need that to do the assessment and to be more accurate in the assessment part. But of course, the main core of the project will not be, I think, in all the projects of this cold topic, is not to do database on hazard assessment of polymers. In some cases, we produce some data that will be available, of course, yes. But yeah, in public databases and the ECA and all this, of course, you don't have that because the polymer is not. And I don't think, and that's, I want to point out that the SSbD is not an instrument to push regulation yet. We will wish to have the regulation pushed, but it's not yet there.
Talking about producing data in your project, especially for the in vitro testing and so on, do you have found any difficulties producing this data for polymeric materials in front of other more classical approaches for chemicals, Javier?
Yes, because usually when you are testing the toxicity of a certain material in vitro, usually you are following a test guideline or an ISO standard, and these guidelines are not fully compatible with mainly materials or chemicals, let's say, that cannot be soluble or well dispersed in the test media that you need. So, for example, as it happens also with, for example, nanomaterials, with polymers, when you try to redisperse these materials and trying to keep the homogeneity of the dispersion during all the assay time, you really find difficulties regarding this, because, for example, polymers tend to agglomerate just because of their physicochemical properties, and you need to stabilize them, but you also need to see if this stabilizer that you are using is compatible with the guideline, compatible with the testing organism or testing system, is not affecting the testing organism. So it kind of it is quite difficult to know how to exactly assess these materials, the polymers, in order to get reliable data and data that has a good quality.
And which strategies have you followed to overcome these problems?
We have used different surfactants. We have found some biocompatible surfactants that allow us to redisperse the material without affecting the testing organism. We also apply sonication, because sonication helps us to redisperse the material, even though sonication could affect polymers in a way it's not highly possible, but it may kind of affect the structure. I mean, you will be testing 99% of the polymer, but you will have a byproduct. But we are trying to use these two main strategies. We also try to apply a small quantity of ethanol to the solutions that in a concentration that, for example, our cells are not being affected by this ethanol, but it helps the dispersion of certain polymers because of the organic. You make it more organic compatible. So these are some of the strategies that we are applying, and we try to choose the best one for the polymer or the material that we are testing.
Okay. So we can go with the next part. We have been commented before, but it's obviously the lack of resources, the lack of data that we need. Socorro, there is some, I don't know, some database or some resource that you missed a lot for the assessment of polymers, or that you I wish that this kind of resource exists for polymers, because there is only for chemicals, for instance. I don't know.
Well, I guess to the same answer, no? It's like all all the data missing is always key for the assessment, and the production of data and changing protocols and adapting protocols to produce data that is useful for and reliable is always a difficult. But I think that's the main issue is to produce data that is not available, and to get the data sources that are possible for do the assessment, and especially I guess also for LCA, that the people from sustainability also has their problems on the inventory data that is not there, the impact assessment factors and all that, that they also find difficulties into doing the assessment reliable as well because of that. And as I said, there's no resources enough in these projects to produce all the data needed. Because you have so many other things to do in the project that at the end you cannot produce or focus a lot in this part, which has not been considered as difficult as then when you are running the project, and you realize that you really should put more resources in the part of producing data, I guess.
Yeah, especially at least for our case, we are very focused on the development of in silico models and this machine learning to predict any kind of toxicity is really difficult, because there are only few polymers with toxicity values, and these toxicity values perhaps are not related with the polymer itself, perhaps with other things, or even this kind of assessment are more focused on new polymers, but you only want to modify one polymer, and then the applicability domain of these polymers, there is no data for that, because you want to for this modify cellulose, okay, biocellulose, and the only data for the toxicity of new polymers is only very new polymers that has been developed recently, but is not closer to other polymers like cellulose, and it's really difficult to create these models. So at least for the this kind of QSAR models that are very they are very useful for other SSbD assessment, like chemicals or even kind of materials. For this part, is really difficult to create this model for this lack of data. So the final part is what are main lessons that you have learned for applying this project. If you start the project again tomorrow, what will be the difference in your procedures, or even if you address this topic from another perspective? I don't know what are the main lessons that you have learned applying this SSbD framework for polymers. Javier?
In my case, I think that something really important that maybe was not considered from the beginning is trying to establish a workflow, a concrete workflow for I'm going to, for example, analyze the polymer, the monomer, and I'm going to also try to apply an aging strategy in order to know how is the plastic going to be degraded in natural conditions or recreated natural conditions. And also trying to not forget or trying to take focus on also what are the parts or the fractions of sizes or shapes that will be most likely to be found, and also trying to take a look on them to generate or understand better the hazardous properties and also the physicochemical properties that allow us to drive better the risk assessment.
Yeah. In your case, Socorro?
Yeah, for me, I think one of the things that were a lesson learned, and also thing to that it was working really well, is to really collaborate internally with all the actors and also all the teams of experts that are in the different fields to exchange the knowledge that we have on the specific cases. So I think this was something that it took quite some time in the project, but I think it was the most successful decision that we made. And it worked really well, and especially now you see it in the scoring system that we are developing, that all the teams are working in the different expertise to get to this scoring system. So it's easier when you have a group of people that is driving the work in one dimension and the other, and then there is an interaction with all the other parts. The other thing that we learn is also that it is really important to consider all the value chain steps, and what we were missing and focusing was also these hotspots and the emissions happening during the value chain, which is at the end what will be impacting the environment and the human health. So it will be important to know if what we will have, what the human and the environment will be exposed to is an additive, is the microplastics or not, because in some cases, in some applications, there's no to be worried about any hazard of the polymer, because the polymer will not be in contact with any human or environment during the use phase or the end of life. But this, you have to ensure that you are really targeting what is emitted, or what is the exposure relevant material that you have to really test. Because of course, if you focusing on the polymer itself, or the alternative that you are doing itself, which is polymer based alternative, and you focus on hazard, but maybe you never be exposed to that, or any additive that, since the additive is integrated in a way that doesn't get out or doesn't get in contact with any human or environment species, then why should we be worried? So I think for us, there is a lot of work on these hotspots and activities and exposure scenarios that were key also to guide the hazard people to say, don't be worried about this, but be worried about this additive that is the one that is releasing. So that's the maybe that's the problem in the use phase, or the recyclability process that you are now proposing in this project, that maybe this recycling process, the workers are really exposed to something that comes from the process more than the polymer itself, alternative polymer itself. So these things, I think, are things to learn. And I think, of course, time is limited, and I think always we put a lot of cases. That is a lot of materials in the project, so you cannot go in deep in all of them, and that's a pity. But I think the strategy and the structure that we follow was quite a successful one at the end. But of course, we see the limitation of time.
Yeah, of course. From my case, I think that is very related with Socorro said. That is, sometimes the polymer itself is not the problem. Is what the impact of the polymer in the life cycle and in the value chain, because perhaps to ensure the functionality of this polymer, we are using other additives, or what happened with this polymer once we have to eliminate it in the end of life, or even in the recycle process, because there is no potential exposure of this polymer to human people during the using, but perhaps we will have some kinds of secondary products, byproducts, microplastics that we are introducing in the life cycle, that there are no, they were not there before. So and perhaps especially this kind of byproducts or this kind of of microplastics were more hazard than others from other polymers, for instance. So we have to think not only in the polymer itself, but all the surroundings of the polymer. Okay, so there is anyone, anyone that wants to ask anything or any question from the audience? Okay, if not, we can close this workshop. Thank you again for joining us. And I hope that it will be very interesting for you. Thank you.